Uh-oh. You saw my physics. All right. That's not what I'm going to do. Now I'm going to do calculus. 5-1. Some problems. First ones we're trying where we're going to start, we have in the past, I guess, somewhat disrespectfully called this first half of section of chapter 5, analyzing the crap out of functions. I think that's a fair description. Using calculus, I should say. Analyzing the crap out of functions using calculus. So number 1, in each part, sketch the graph of a function with the stated properties and discuss the signs of f prime and f double prime. So for A, I want a function that's concave up and increasing everywhere. So it's concave up and increasing everywhere. So like this, no, that wouldn't work because it's decreasing. So what you would have to have is something, I mean, I have a library of functions just kind of ready to go in my mind. You probably do too. So that would do the trick, right? It's increasing, although it's increasing very slowly here and concave up. There's other things that you could draw, but the idea is it couldn't ever come back up like this. So I think you'd have to have, you wouldn't have to have an asymptote. You could construct one otherwise, but that's just one way of handling that. How about one that's concave down and increasing everywhere? Concave down and increasing. So I guess that would be like that. I don't need a y-axis, right? Actually, I don't really need any axes, do I? And it would also have to, it would never come back down because that would be a maximum and then it would be decreasing after that. And they said it's increasing. C, function is concave up and decreasing. So concave up, bending up but decreasing. So hold on, this is just like a picture of those 4 little things from the little chart I made in your notes. And then D, the function is concave down and decreasing. So that's bending down and going down. So that's the different possibilities. Those are the 4 combinations of those things. All right. Number 3, use the graph of the equation in the accompanying figure to find the signs of dy dx and the second derivative at the points a, b, and c. I'll make a little chart here. How about that? So here's the sign of dy dx. And then the sign of the second derivative. Let's see, so the sign of the first derivative is just whether it's increasing or decreasing, because I am looking at the graph of the actual function. So A is decreasing, B it's increasing, and C it's decreasing again. And then the second derivative is the which way it's bending, whether it's like part of this, now either half of that, right? It could be this or this, that's positive second derivative, or is it part of this, right? Usually what you're looking at will be 1/2 of those. But these ones, if it's part of a cup, then it's concave up. If it's part of a frown, then it's concave down. Oh my God, would you believe that I just made that up right now? I swear to you, I just made that up. If it's part of a cup, it's concave up. If it's part of a frown, oh, then it's concave down. All right, there you go. Say that 30 times. So let's see, at A we've got part of a cup, so it's concave up, and then B, those are both the 2 halves of the frown, so it's concave down. Oh, that looks like a sad bunny. All right, enough of that. 7. Part of a cup, it's concave up. It's part of a frown, it's concave down. In each part, use the graph of y equals f of x in the accompanying figure to find the requested information. Requested information. Find the intervals on which f is increasing. Okay, so that means the actual, this is the picture of the function itself. So where is it going up? It's going up from 4 to 6. Use that interval notation. And that's it. And then how about where it's decreasing? Well, it's decreasing everywhere else. That's 1 to 4 and 6 to 7. Where are the intervals where it's concave up? So part of a cup, so that's going to be 1 to 2, that's upward bending, although it changes its mind from 2 to 3. And then from 3 to 5, that's cuppy, and that's it. And so for D, where it's concave down, that's all the other intervals, so 2 to 3, and 6 to 7? No, 5 to 7. That's some frowny parts. And then find all values of x at which f has an inflection point. The definition of an inflection point is where the sign of the second derivative changes. In other words, where it goes from concave up to concave down. That happens at x equals 2. It changes from concave up to down. And then at 3, it changes from down to up. And then at 5, it changes from up to down. All right. Let's see. What's next? Number 11. Okay, now we've got some actual functions here. I'm going to go ahead. I know what's coming here, so I'm not even going to read the directions yet. I'm just going to go ahead and find the first derivative and the second derivative. Because I know I'm going to be doing these things. So the intervals on which f is increasing, decreasing, and where it's concave up, concave down, and the x coordinates of all inflection points. So it's actually the same as those parts, isn't it? Okay, so what I'm going to do, I'm going to find the zeros of these, and I'm going to make this little sine chart. So the only place where this is 0 is at 3/2. Now I'm going to make a little mark here. Instead of making number line style that goes all the way through, I'm just going to make it on the top. This is just one way of doing this. You don't have to organize your information this way, but I think it's a okay way of doing it. And then this, if you try points on either side, if you plugged in 0, for example, you get -3. It's negative on this side, and then positive on this side. Of course, 0 right there. Now the second derivative is just always positive. It's never equal to 0. It's just 2 all the time. Okay, so this little sine chart, excuse me, that's not the answer to any question, but it's a nice way for us to organize the information so we can report these answers. Where is it increasing? It's increasing, that's the sign of the first derivative, tells us increasing or decreasing. It's increasing from 3/2 to infinity. Where is it decreasing? It's decreasing from negative infinity to 3/2. Where is it concave up? Is that what I want first? Yeah. Where is it concave up? Everywhere. Where is it concave down? Nope. Nowhere. Where are the inflection points? There are none. An inflection point is where the sign of the second derivative changes, and that's not happening. Number 23, e to the negative x squared over 2. All right, what's the first derivative of that? It's the derivative of e to the whatever is e to the whatever times the derivative of what's inside. Okay? And then the second derivative, I'm leaving a little space there so I can, if I decide I want to find the zeros, that is, if I set that equal to 0, well, sorry, I got distracted by my own self there. So just looking at this is in factored form, and e to the something, it doesn't matter what that something is, e to the power of something cannot ever be 0 or negative. You can't raise a positive number to a power and get it to be 0 or negative. So this is never equal to 0. If you're thinking about like factoring things, and then you've got like, you got your x minus 1 and your x plus 2 equals 0. And you're like, oh, what makes this 0? 1. What makes this 0? Negative 2, and that's your answers. So what makes this 0? Nothing. It's not possible. What makes this 0? 0 does. So this is equal to 0 at x equals 0. So when I make my little sine chart, that will be there. And then since this is e, positive number to a power, that's never going to be negative. So I don't have to pay attention to the sign of that at all when I'm making the signs here. So since this is negative x, if I plug in a negative number, it's actually going to be positive. And then if I plug in a negative number, that's going to be positive number, it's going to be negative. Okay, so sorry, I got distracted there. So let's go ahead and find the second derivative. Going to have to use the product rule for that. So the derivative of the first, well, we already did that. That's this whole thing. So that's negative x times e to the negative x squared over 2. That's the derivative of the first times the second plus the first times the derivative of the second. All right. I would like to know where that's equal to 0. And to get a meaningful or workable thing here, I need to do some factoring. I'm going to factor this out to the front. Negative x times negative x. And then a minus 1 here. So that is never going to be equal to 0. I don't really even have to worry about that in terms of determining where sign changes happen, where the zeros are. So 1 and negative 1. And when I'm figuring out the signs, what's going on here with the second derivative, I don't need to worry about this. That's always positive. So the signs of this, well, I mean, that's an upward opening parabola. So it's going to be plus, minus, plus, right? I mean, this looks like this. It's positive, negative, positive. You could go ahead and put in numbers and test them if you want, but any insight you have into these things, any leaning you can do on prior math knowledge, it's all good, healthy to do it that way. All right, so are I answering the same questions? I am. So where is it increasing? From negative infinity to, sorry, that's a comma, 0. Where is it decreasing? From 0 to negative, positive infinity, just kidding. Where is it concave up? From negative infinity to negative 1, and from 1 to infinity. Where is it concave down? From negative 1 to 1. And where are the inflection points? Inflection point, the definition of an inflection point is where the sign of the second derivative changes. Positive to negative or negative to positive. So I have an inflection point at negative 1 and at 1. Great. Do you know what that function looks like? We didn't graph it, but that is a sort of template for the normal curve, like the so-called bell curve. It's not the normal distribution, but it's very closely related to it. So if you're interested in statistics and stuff like that. So here, if you look at what's going on, sure enough, it's increasing from negative infinity to 0, and then it's decreasing, and then it's concave up, bending up, and then bending up again, and then from negative 1 to 1, it's bending down, and there's the inflection points. All right, super. 29. What do we have? New section. So analyze the trigonometric function and stating where it's increasing, decreasing, concave up, concave down, and inflection points. Why didn't they just put this in the same set? I guess they're giving us an interval. I was like, should have just kept the same directions. So f of x is equal to sine x minus cosine x, and I'm only interested in from here to here, which is probably good because this should be a periodic thing, so it's got like infinitely many places where it's increasing and then decreasing and so on and so on. So thanks, guys, for sparing me writing an infinitely long answer. The derivative is that. And the second derivative is that. So where are these things equal to 0? Let's see if we can do that. Actually have to do some trigonometry here. Now there's a lot of ways that you can do this. Two suggestions. One would be to move the cosine to the other side and realize, then divide by that. So you realize that that's the same as tangent x equals -1. Or maybe, possibly, I guess in my opinion this is kind of better, to look at this and realize, oh, this is only true if sine and cosine add up to 0. That's only true if they're equal to each other but opposite in sign. So where does that happen, that sine and cosine are equal to each other? Well, they're equal to each other in magnitude at those 4 places, but here and here they have the same sign, and here they have opposite signs. So it would be at 3 pi over 4 and 7 pi over 4. But we need the ones that are in this interval. So if you think about starting at -pi and then going around to positive pi, we're going to hit 2 of them, but it's not 7 pi over 4 here. It's -pi over 4 and 3 pi over 4. Those are the places where the first derivative is equal to 0. So here, going from -pi to pi, my first derivative on top, second derivative on the bottom. So 0 would be right in the middle there. And let's see, -pi over 4 would be up here, and then 3 pi over 4 would be up here. And what are the signs of this? Well, maybe we need to test points. So if I tried 0, for example, in between here, then at 0, I have the cosine of 0 is 1 plus that is 0. So this is positive in here. And then here, I could just test this endpoint here. I could do -pi over 2. That would work. The cosine of -pi over 2 is 0, and the sine of -pi over 2 is -1. So that's negatives down there. We kind of expect to see sign changes here. Every once in a while, not too infrequently, we see special cases. Hopefully there's going to be one in this homework somewhere. Maybe, we'll see. If not, we'll see one soon, where you don't get a sign change, either here or in the second derivative. But most of the time we do. Not to the point where you would just like find one of them and then just automatically alternate across your zeros. I don't think that's a good idea. Okay, and then f double prime, when is negative sine plus cosine equal to 0? Well, that's when they're equal to each other. So that's going to happen here and here, and then going from negative pi, the first one we hit is at -3 pi over 4, right here, and then around here, positive pi over 4. And if I plug 0 into this, I also get positive. 0's in this part of the interval. and they're going to alternate. You can double check those if you want. Okay, so same questions, right? Where's it increasing from negative pi over 4 to 3 pi over 4? Where is it decreasing from negative pi to negative pi over 4, and from decreasing from 3 pi over 4 to pi? Where is it concave up? From negative 3 pi over 4 to pi over 4. Where is it concave down? From negative pi to negative 3 pi over 4, and from pi over 4 to pi. And where are the inflection points? They're at x equals, those are the places where the sign of the second derivative changes. Right? What if the sign of the second derivative was 0, but it didn't change sign? Is that an inflection point? No. You have to have a sign change of the second derivative for it to be an inflection point. And last one is 35. In each part, sketch a continuous curve with the stated properties. So for part A, I got f of 2 equals 4. That's a point. F prime of 2 is 0, so that means the tangent line is 0 there. And f double prime of x is positive, so it's concave up everywhere. So I guess if it's going to go through this point, and it's going to have a slope of 0 there, and it's concave up everywhere, then it must be like grazing that, kind of like that. Right? Like it couldn't be concave up everywhere. I guess it could be. So that's one way of, oh no, I was going to say it could be like that exponential thing, but that wouldn't have a slope of 0. So I think it has to be that. Something like that. It's interesting to think about what the criteria was there. We'll get into this soon. But this that the derivative was 0 and the second derivative was positive forced there to be a minimum there. That's worth noting here. For the second one, got the same point, 2, 4, and the derivative is 0, so it's going to have a horizontal tangent line there. And the second derivative is negative when x is less than 2. It's bending down. And the second derivative is positive when x is greater than 2. So it looks kind of like a cubic function that goes through that point. That's an interesting kind of point. Some folks call that like a saddle point here, where the derivative is 0 there, but it's not a maximum or a minimum. It was like trying to be a maximum, and then it changed its mind and went back up. But just at that spot right there, the derivative is 0. Slope of tangent line is 0. All right, for part C, same point, again, at 2, 4. The second derivative is, let's see, it's less than 0. It's negative when x is not equal to 2. Okay, so it's negative when x is not equal to 2. That means it's bending down. So maybe I'm imagining something like that. And the limit as x approaches 2 from the positive side of the derivative is positive infinity. Okay, so let's think about this. As I approach 2 from the positive side, the derivative becomes closer and closer and closer to positive infinity. So positive infinity is things that have slopes like super steep this way. So it must be like right at this point is like coming out of there, and then they've got to start backing off there because it can't go straight up, right? So those are slopes that are positive very close, very, very, very large, approaching infinity, and then tapering off like that. And then on the other side, the limit as x approaches 2 from that side, the slopes are approaching negative infinity. And it's supposed to be concave down, bending down everywhere. So it is. Now, of course, it would not have the second derivative at 2. Does not exist. It doesn't have any concavity there at that sharp corner. So that's interesting. That's a tricky one. And that's all. That was a good exercise.